Hello dear students and welcome back to our discussion about noise. In this particular video, I will discuss to you quantitative noise analysis. So in this topic, we will discuss the following metrics or figure of merits used to evaluate the noise performance of a portion of the communication system. For example, we will discuss the signal-to-noise ratio, the noise factor and noise figure, the equivalent noise resistance, and noise temperature. So these are the ways on how we can measure the amount of noise present in a communication system. Or for example, the amount of noise produced by a particular amplifier in a communication system. Okay? So, let's start with the discussion of the signal-to-noise ratio. So, the signal-to-noise power ratio or simply signal-to-noise ratio sometimes is called SNR, signal-to-noise ratio. Pero pag SNR, baka maisip mo magsha-shopping ka, kaya S over N na lang. No? Ano ito? It is simply the ratio of the power of the signal to the power of the noise. So, the signal-to-noise ratio is the ratio of the power of the signal to the power of the noise. So, of course, we can expect that the amount of noise present is just small. So, the desirable value of the signal-to-noise ratio would be high. The higher the value, the better. Okay? So, again, PS represents the signal power in watts and PN is the noise power in watts. Okay? And remember, a higher value of S over N is desired. Okay? Because that indicates lower amount of noise. Okay? So how do we express the signal-to-noise ratio? The signal-to-noise ratio is unitless. However, it can also be expressed in dB. So how do we express the signal-to-noise ratio in dB? We simply get 10 times the log of the signal-to-noise ratio. Okay? So this will give us the dB value of S over N. Okay? So tandaan po natin, kapag ka ito ay ratio, unitless iyan. Kapag ka po iyan ay logarithmic, siya ay naka-dB. Ano? Let us have our first example. If you have 100 millivolts of signal and 10 millivolts of noise, both across the same 100 ohm load, what is the signal-to-noise ratio in dB? So, if we will get the signal-to-noise ratio in dB, so that will be 10 log of the power of the signal divided by the power of the noise. So, yan yung ating S over N. Okay? However, we are not given the power of the signal and the power of the noise. Rather, we are given the voltage. No? So, we have the 100 millivolts signal and 10 millivolts noise. And they are measured across the same resistance. So, we know that the formula for finding power in terms of voltage is V squared over R. So, if we will use this formula and replace PS and PN with V squared over R, we will get 10 log of V squared over R for the signal divided by V squared over R for the noise. But, for both the signal and the noise, the voltage are measured across the same 100 ohm load. So, the resistors will cancel, leaving us with V of the signal squared divided by V of the noise squared. Okay, which can be expressed as 10 log of Vs over Vn, and both of them squared. Okay, so of course, we can simplify this by applying the properties of logarithms. This becomes 20 log of Vs over Vn. So, ayan. Kapag voltage yung given, remember, nagiging 20 yung multiplier natin. Okay? So, we can now calculate the signal-to-noise ratio. So, 20 times the log of, so we have 100 millivolts divided by 10 millivolts. So, magka-cancel ang mga milli. 100 divided by 10 is 10. Log of 10, of course, is 1. Times 20, of course, we have 20 dB. So, hindi mo na kailangan ng calcu kasi simple lang naman yung mga given parameters dito. Kaya i-mental math kahit may logarithm. Okay? So, in this problem, we're able to get a signal-to-noise ratio of 20 dB. Okay? So, normal naman yan. Kapag sa isang system, ang signal-to-noise ratio mababa, halimbawa, 10 dB, medyo mababa yun. Ibig sabihin, malaki na yung present na noise. Okay? Now, let us go to the next slide to discuss another topic. So, this time, we'll discuss the noise factor and the noise figure. Actually, these two quantities are very much related. Yung isa, ratio. Yung isa, dB value ng ratio. Okay? So, let's start with the noise factor. Noise factor is the ratio of the signal-to-noise ratio at the input to the signal-to-noise ratio at the output. So, ano ibig sabihin nito? Ang noise factor ay ratio ng dalawang S over N. Ano yun? S over N at the input divided by the S over N at the output. Okay? So, it's the input divided by the output. Now, if we get the dB value of the noise factor, we will get what you call the noise figure. Okay? Madali lang pala yun, ano? Yung noise factor, pag kinunan mo ng dB value, so yun yung 10 log of F, yes, that is called the noise figure. So, if it's noise factor, it's unitless because it's a ratio. But if it's noise figure, then its unit is dB. Okay? So, that's the dB value of the noise factor. Lagi po nating tatandaan yan. So, ano bang itsura niyan? Para halimbawa, kung ito yung amplifier mo, natural, meron kang input at saka output. Sa input, may signal power at may noise power. Sa output, may signal power and at the same time, may noise power din. Ano? So, ano ba ang signal power at the input? Ano ang noise power at the input? Yun ang signal-to-noise ratio sa input. Ano? And at the output, may makukuha kang signal. At the output, meron ding noise. So, makukuha mo yung signal-to-noise ratio sa output. Kapag pinag-divide mo yung dalawang signal-to-noise ratio, input divided by the output, ang makukuha natin ay ang tinatawag na noise factor. Ano? Yung dB value ng F, yun ang NF or noise figure. Of course, naka-dB iyon. Okay? So, let us have an example. Here, we have a transistor amplifier that has a measured S over N of 10 at its input and 5 at its output. Calculate the noise factor and the noise figure. So, madali lang ito, ano? Kung makikita natin, ang noise factor ay yung signal to noise ratio at the input divided by the signal to noise ratio at the output. So, given naman yun ano? 10 ang signal to noise power ratio, the input. So, divided by 5, which is the signal to noise ratio at the output. So, the noise factor is 2. Ano? Kung gusto mong makuha ang kanyang dB value, yun yung NF. So, we have 10 log of 2. Of course, gamitan natin yan ng calcu. Ano? 10 log of 2. This gives us 3 dB approximately. So, ayun. Yung noise figure which corresponds to a noise factor of 2 is actually 3 dB. O, di ba? Dali lang. Sobrang dali. Ano? Now, ano bang gusto nating value ng signal to noise ratio? At the input, gusto natin ito ay malaki. Di ba? At gusto rin natin ang signal to noise ratio sa output ay malaki. So, ano dapat ang makuha nating noise factor? Actually, kung ang isang amplifier ay ideal, it doesn't add noise to the signal. Hindi siya nag-a-add ng noise. Kung yun ay amplifier, the amplifier is noiseless, it doesn't add noise. So, if that is the case, yung makukuha nating noise factor is 1. So, this is the ideal value of the noise factor. So, kung tatanong mo naman, ano ang ideal value ng noise figure? Di yung 10 log of 1, alam naman nating 0. No? 0 dB. These are the ideal values of the noise factor and the noise figure. And this is true if your amplifier or circuit is noiseless because it doesn't add noise to the system. Naiintindihan po ba? So, ano palang ibig sabihin ng noise figure? Kung malaki ang noise figure, then yung amplifier na yon or yung circuit na yon nagdagdag ng considerable amount of noise. Kung napakababa ng noise figure, then yung circuit or amplifier ay nag-generate lang ng maliit na amount of noise. So, remember, the ideal value is 0 dB. So, the closer to 0, the better. So, if it's noise factor, the closer to 1, the better. So, walang noise factor na less than 1. Yan ay yung minimum. So, for normal amplifiers, typical amplifiers, F is greater than 1 and NF is greater than 0. Okay? But for ideal systems na noiseless, ang noise factor ay 1 at ang noise figure ay 0. Diyos ko, walang alam. Next, the input to an amplifier has a signal-to-noise ratio of 100 dB and an output signal-to-noise ratio of 80 dB. Find the noise figure and the noise factor. So, kanina, yung signal-to-noise ratio natin given as ratio. But this time, they are given in dB. So, kung dB, anong gagawin natin? I-convert pa ba natin yan sa noise factor para makuha ang noise figure? Hindi na actually. Pagmaminusin mo na lang yan. Bakit? Kasi ganito yan. Kapag ang signal-to-noise ratio mo ay naka-dB na, yung signal-to-noise ratio sa input, no, divided by the signal-to-noise ratio at the output, ang makukuha mo na dyan, yung noise figure in dB also. So pag ang dalawang signal-to-noise ratio pala naka-dB na, pag maminusin mo lang, no, input minus output, ang makukuha mo na noise figure in dB. Yes, exactly. So gawin natin dito, no. Ano ang signal-to-noise ratio sa input? 100. Minus the signal-to-noise ratio at the output, 80. Ayan. So, natural ang sagot. Baka magkalkyo ka pa, ha? Grabe ka naman kabobo. No? So, 20 dB lang yan. No? 20 dB ang noise figure. Okay? So, ngayon, ano naman ang noise factor? Makukuha natin yan mula sa 20 dB. Diba? Because 20 dB is 10 log of F. So, para makuha mo yung F, that's 20 divided by 10, which is 2. And then, anti-log, which means 10 raised to 2 or 100. O, di ba? Ang dali lang. Again, kapag kaganyan mga kasimple ang kinocompute natin, hindi na tayo dapat nagkakalkyo. Para naman nagiging matalas yung ating mental math. Nagagamit natin, nasa-sharpen natin ang ating mental math. Okay? So kapag hindi mo na alam yung mga log, halimbawa, log of something that is not powers of 10, saka mo i-calculate yun. No? Pero log of something na powers of 10, madali lang yan. Diba? Kung ilan yung 0, yun na yun. Log of 100, 2. Log of 1,000, 3. Diba? Log of 10,000, 4. Okay? Next example. For a non-ideal amplifier having the following parameters. O, ayan, non-ideal yung amplifier mo. So, that means, nag-a-add siya ng noise. O, tingnan ninyo. Yung input power daw ay 0.2 nanowatts. O, napakaliit, jutyness. Yung input noise power, mas maliit. 2 AW. Ano yung AW? Atto watt. Di ba yung atto to the negative 18 yun? Yes. Sobrang super jutyness niyan. Di ba? Power gain, 1 million. O, malaki. Tapos, yung system nag-generate siya ng internal noise na 6 picowatts. Ay! Shit! O, ano namang meron? Ano daw ang signal-to-noise ratio at the input, output, at ang noise figure. Okay. So, kunin muna natin yung sa input, no? At the input, S over N equals 10 log of the input signal power is 0.2 nanowatts divided by input power is 2 atto watt. 2 atto watt. Okay. So, with the use of a calculator, gamitan natin yan. 10 log of 0.2. Ang nano ay to the negative 9. Samantalang, ang atto ay to the negative 18. And then, poof, ang sagot, 80. So, we have 80 dB of signal to noise ratio at the input. Okay? So, ang output, makukuha natin ngayon because the output, remember, is equal to the input times the gain. O, ilagay natin dito. Output equals input times gain. So, therefore, ang power ng signal sa output ay equal sa, we have 0.2 nanowatts times the power gain, which is 1 million, no? 1 times 10 raised to 6. Diba? So, we have 0.2. Nano is to the negative 9. And this is to the 6. Negative 9 plus 6 is negative 3. Diba? So, 0.2 milliwatts. Okay? Now, how about the noise at the output? The noise at the output is the noise at the input, which is 2 attowatts times 1 million. 1 times 10 raised to 6, ano? Plus, yung internal noise na 6 picowatts. Okay? So, compute natin yan, ano? So, we have 2 times 1 is 2. Atto is to the negative 18. Negative 18 plus 6 is negative 12. So, pico. No? So, we have 2 picowatt plus 6 picowatt. We have 8 picowatts. So now, we can determine the signal to noise ratio at the output. Okay? So this is 10 log of 0.2 milliwatts divided by 8 picowatts. And the answer is 73.98 approximately. So this is 73.98 dB. Okay. So, nakuha na natin ngayon ang signal to noise ratio sa input at sa output. Naka-dB pa sila. Ngayon, ano naman ang noise figure? O, ang noise figure, makukuha natin difference lang yan ng signal to noise ratio sa input minus yung output. So, we have 80 minus 73.98. O, diba pag pinag-minus natin yan, 6.02. Diba? 6.02 dB. Okay? So now, we're able to solve the problem. Now, nakuha na natin ang signal to noise ratio sa input, sa output, at ang noise figure. No? So, ang noise figure niya, 6.02 dB. Medyo malaki. 6.02 dB. Kasi ang ideal niyan, remember, 0 dB. Now, let us discuss another topic, the equivalent noise resistance. So, ito, hindi siya talaga isang tunay na resistor, hindi siya na measure ng ohmmeter. Ano? This is a fictitious resistance that we use to indicate the amount of noise present. So, if we have a system of amplifiers in cascade, so connected sila in series, just like this, ano to? Ito yung noise voltage na na-generate nung resistor na R1. At ito yung amplifier, okay, na may gain na A1. Next, for the second stage, we have a noise resistor R2 which generates the noise voltage VN2. And it is followed by an amplifier whose gain is A2, etc. Ano kung ilan man sila. So, dito sa ginawa kong example, meron tayong tatlong stages. Ano? O, ano gusto nating computein dito? Gusto nating makompute yung buong system na yan. Ano ang kanyang equivalent resistance? No? The equivalent noise resistance. So, hindi ko na i-derive, pero ito yung formula. Ano po? Kung gusto ninyo, ang derivation nito ay exercise. You can find the derivation in books like yung book ni Miller, may derivation doon. Yung book ni Kennedy, meron doong derivation ng noise resistance. Okay? So, the equivalent noise resistance is given by R1, ito yon, plus R2 over A1 squared. Kung mapapansin natin, yung denominator ng R2, naka-square siya, oh. Tapos yung third term, R3. At ang denominator niya, product naman ng dalawa na naka-square. A1 squared times A2 squared. So, dun pa lang sa pangalawang term, pag yung R2 dinivide ko ng something na naka-square, liliit na yon. Diba? So, that means, this second term is significantly much smaller than R1. Why? Kasi ang R1, wala namang divisor yan. Yung R2 may divisor eh. Yung A1, in-square mo pa. E di lalo na yung third term. Kasi yung R3 niya, ang divisor mas malaki. A1 squared times A2 squared. Yes. So, anong sinasabi sa atin ng formula na ito? Simple lang. Ano? Ibig sabihin yan, kung meron kang amplifier system connected in cascade, yung unang stage ang may pinakamalaking ambag doon sa equivalent noise resistance. Why? Kasi yung second, third, and fourth, etc., palaki ng palaki yung denominator nila. Kaya yung ambag nila doon sa formula, lumiliit ang value. That's why we say that it is the first stage that has the most effect in the equivalent noise resistance. Siya ang pinaka nakaka-apekto doon sa equivalent noise resistance ng isang amplifier system connected in cascade. Okay? So, tandaan po natin yung formula. Now, to demonstrate how to use this formula, let me give you this example. No? The first stage, may two-stage amplifier. O yan, dalawang stage lang siya ha. Yung unang stage ay may voltage gain na 10. Ayan no, 10. Sunod, meron daw siyang 600 ohm na input resistor at 1,600 ohms na equivalent noise resistance. At meron siyang 27 kilo ohm output resistor. Yung second stage niya naman, not 3, it should be this, no? These values. These values are 25, which corresponds to the gain, 81 kilo ohms, which corresponds to the input resistor, and 10 kilo ohms corresponding to the equivalent noise resistance. At yung 1 mega ohm, yun yung output resistor ng second stage. Ngayon, anong hinahanap? Calculate the equivalent input noise resistance of this two-stage amplifier. Computin din natin ang noise power na kanyang mapuproduce and the total noise voltage. Okay. So, i-drawing muna natin. Halimbawa, ito yung dalawang amplifier stages. Ano, ilagay natin ngayon yung mga resistances. No? So, ito daw ay may gain na 10 at ito ay may gain na 25. Tapos, 600 ohms na input at 1.6 na noise resistance. Ano itsura nun? Unahin natin i-drawing yung equivalent noise resistance kasi hindi naman talaga siya tunay na resistor. No? Ito ngayon yung actual input resistance. Yan. Ito yung 600 ohms na input resistance at ito naman ang 1,600 ohms na equivalent noise resistance. So, they are drawn in series. Okay? So, sa output, natural malamang may nakaparallel dyan yung ating load. Okay? Ito ngayon yung load na magkano? 27 kilo ohms. Now, ngayon, isunod natin yung katumbas ng 600 ohms. Yun yung 81 kilo ohms. Okay? So, this 81 kilo ohms is the input resistor of the second stage and ito naman yung 10K na equivalent noise resistance ng second stage. O, lagyan natin ng label, 81K. This is 27K. Itong dalawa naka-ohms yan. Ano? So, yung output stage ng second stage, may output resistance na magkano? 1 mega ohm. Ayan. So, ngayon, anong sunod? Makompute na natin ang equivalent noise resistance at the input. Pero dapat i-simplify muna natin, ano? Nandito yung R1, nandito yung R2, remember, at nandito yung R3. So kung titingnan natin yung previous slide dito, 'di ba? Ayan R1, R2, R3. Kung two stages lang. So ano yung R1, R2 at R3? Simplify natin, guys. Ano? Yung R1 ay obviously naman, ang R1 ay yung series combination nito. 600 plus 1,600 is 2,200. O baka mag-calculate ka pa doon, ha? Okay. How about yung R2? Ang R2, parallel combination nung 27K at saka 81K. And then after that, yung combination na yun nakaseries sa 10K plus 10K. Okay. So, pag kinumpute natin yung R2, gamit ang calcu, So, we have 27 kilo ohms na nakaparallel sa 81 kilo ohms equals inverse equals. So, 20 to 50 plus 10k pa, no? Plus 10 exponent 3. So, magiging 30 to 50 yan, ano? So, we have 30, 250 ohms or 30.25 kilo ohms. And of course, yung R3, mag-isa lang naman to. So, yun na yun. Ang R3 mo, yun na yung 1 mega ohm. Okay, so now, hanapin na natin ang equivalent noise resistance. Ano po yun? E di yung R1 mo na 2,200 plus yung R2 mo. Yung R2 natin na magkano? 30.25k divided by the gain of the first stage. So, 10 squared plus yung R3 which is 1 mega ohm divided by 10 squared times yung second stage, ang gain ay 25. So, 25 squared. So, now, we can get the equivalent noise resistance, 2518.5. No? So, we have 2518.5 ohms. So, yan na po ang sagot. Okay, this is the equivalent noise resistance at the input of this amplifier. So, anong pwede mong gawin dyan? Pwede mo na siya ngayong i-drawing as ganito. Lagyan mo ng noise voltage na Vn. Ito na ngayon yung equivalent circuit niya. Ano? So, this is the equivalent noise resistance and the noise voltage that it produces. Ngayon, ang sabi sa atin, hanapin daw ang noise power. O, madali lang. Kasi ang noise power nito, remember that N equals KTB. Pero wala naman tayong given na bandwidth. Kung may given na bandwidth, makukompute natin yung noise power, which is independent of what we have computed. Okay? Yung noise voltage naman, remember that's square root of 4 KTBR. Ayan. So, since sa formula ng noise voltage, mayroong resistance, yan yung gagamitin nating R, yung na-compute natin. Ano? Pagpalagay natin, halimbawa, ang bandwidth ay 200 kilohertz at a temperature of 310 kelvins. Pagpalagay natin, no? Yan yung conditions. Compute natin ngayon yung noise power, no? Na KTB 1.38 times 10 to the negative 23 times 310 kelvins times the bandwidth which is 200 kilo times 10 raised to 3. Okay. So, the noise power is 855.6, no? 855.6. Ang multiplier is to the negative 18. So, atto watt. Okay? Na kapag kinumpit mo naman ang noise voltage, so square root of 4, ito na yung KTB mo, no? Yung answer natin, no? So, 4 times yung answer na KTB times yung R na magkano? 2518. Okay? 0.5 para mas eksakto. Okay. So, ang sagot, ayan, 2.94 approximately to the negative 6. So, we have 2.94 microvolts. Ayan. So, kung ang resulta na nakuha natin dito ay ginamit natin sa isang system na may bandwidth na 200 kHz at may noise temperature na 310 kelvins, ito ang makukompute natin na noise power at ito naman ang noise voltage. Okay po? So, kung inyong napansin, maliit masyado ang noise power. Minsan yan ay atto, minsan yan ay naka-femto. At ang noise voltage usually ay microvolts or naka-nanovolts. Okay po? Pag ang noise power mo naging millivolts, aba, ay kabahan ka na, napakalaki ng noise na niyan na posibleng maging dahilan para matabunan yung signal. Baka yung signal maging unintelligible na. Or kung digital communications yan, it might cause the data to become corrupted. Okay po? Yes. Ngayon, i-discuss naman natin kung ano kinalaman ng noise resistance sa noise factor. Okay, so ano ibig sabihin nito? Posible na makompute mo yung noise factor kung given ang noise resistance. O ganito ang equivalent circuit niyan. Kung halimbawa, meron tayong receiver. Meron tayong isang receiver, RF receiver, yan natural, meron siyang antenna. At yung antenna natin may resistance. Yun yung RA, resistance ng antenna. Of course, that resistance will generate a noise voltage Vn. So, ito yung noise generator natin. Okay? Tapos, yung antenna yan, ikakabit mo dun sa front end ng receiver. Yun yung amplifier natin. So, yung RT, yun yung input resistance ng amplifier. Tapos, yung A, of course, yun yung gain ng amplifier. At yung RL, yun naman yung load resistance ng amplifier. Okay? Ngayon, anong balak natin gawin? Kukuha tayo ng equivalent noise resistance dito na hindi kasama yung RT. So, we would like to solve for an equivalent noise resistance na hindi kasama yung RT or input resistance ng amplifier. So, anong ibig sabihin nun? Ang i-consider lang natin yung equivalent noise resistance nung sa antenna. Okay? So, that's Rx. Yan yung na-compute natin kanina. Gamit yung formula. Minus yung RT. Again, ito yung total noise resistance minus the resistance due to the input impedance of the amplifier. Why? Because in the succeeding calculations, kailangan natin yung effective noise resistance. Yung effective noise resistance, hindi kasama yung input resistance ng amplifier. So guys, eto na yun. Yung R prime X. Okay? Ngayon, ano naman yung total equivalent noise resistance ngayon? Considering na etong RT. So, hindi natin basta-basta i-add yun. Okay? So, meron tayo ditong isang equivalent circuit kung saan ang galing ito. So, the total equivalent noise resistance is now equal to yung equivalent noise resistance with prime, meaning hindi kasama yung RT, plus the parallel combination of, parallel combination ng RA at saka RT. So, hindi siya ipina-plus lang. Dinadagdag natin dun sa R prime equivalent is a parallel combination of these two. Kaya tinanggal muna natin yung RT para dito natin siya i-consider. Ngayon, ano naman pag nakuha mo yung R na yan? Makuha mo yung R na yan, pwede ka na makapag-compute ng noise factor. Ito po yung formula. Sa pag-compute ng noise factor is equal to 1 plus yung R equivalent times RA plus RT over RA times RT. Actually, parang ito yun Kapag kinuha mo yung resistances niyan, ang makukuha mo ay RA times RT over RA plus RT. Okay. So, reciprocal pala nung resistance ito. Diba? Okay. Equivalent resistance. So, 1 plus R prime equivalent, yung nakuha natin kanina, times RA plus RT over RA times RT. Okay? Ngayon, there are times na nagkakaroon ng mismatch. Ano po ang ibig sabihin nun? Hindi matched yung impedance na ito doon sa RT. Halimbawa, malaki masyado yung RT kumpara sa value ng RA, which is the case in most systems. If RT is much greater than RA, mismatch yung condition natin. We can simplify the formula that F is simply equal to 1 plus Rx prime, ito yon over RA. Why? Because for mismatched conditions, again, this term becomes approximately equal to 1. Why? Because again, RT is much greater than RA. Now, if RT is much greater than RA, then itong RA plus RT over RT nagiging approximately equal sa 1, kaya ito na lang yung natitirang formula. Okay? So again, kapag ang condition ay mismatched, meaning mas malaki masyado ang value ng RT kumpara sa RA, ito na lang ang ating gagamiting formula. Pero kung matched yung condition, definitely, we have to use this one para ang ating sagot ay accurate. Okay? Sige. Parang ito yung problem kanina. Diba? Yes. So basically, yung problem natin kanina, anong ginawa? Calculate mo daw yung noise figure nung two-stage amplifier na yan kung siya ay driven by a generator. Ayan. So kung ito-drawing natin, yung generator niya, ang output impedance daw ay 50. So ito yun, no? Ito yung 50. Tapos ito naman yung amplifier mo. Na-remember magkano ang input resistance? 600. Para bagang yan yung drawing natin ngayon. Tapos ito, connected papunta sa generator mo, no? Ito yung generator at ito yung amplifier. Okay. So paano natin yan isosolve? So remember, ito ay 50 ohms lang. Kung titingnan natin yung drawing kanina, ito yun, no? Yung RA, yan yung 50 ohms. At yung RT, yan yung 600 ohms. So kailangan muna pala nating makompute yung R prime X, no? Yan yung equivalent noise resistance na nakuha natin minus yung RT, no? R prime equivalent is ito yung 2518 kanina minus magkano ang ima-minus ko? 600. So this is how much? 18 ohms. Okay. Tingnan natin. Ito bang dalawa ay matched or mismatched? Ang laki ng difference o 50 ohms at saka 600 ohms. Dahil yan ay mismatched condition, no? Ang gagamitin nating formula sa pagko-compute ng noise factor ay 1 plus yung na-compute nating Rx divided by RA. Solve na natin. So 1 plus 1918 divided by, ang RA ay yung 50. Remember? Kasi nga ito, yan yung RT mo. So sa calculator, we will get 39.36. 39.36. So walang unit yan. Kasi siya ay noise factor. Ano? Ang hinahanap ay noise figure. So yung NF ay 10 log of 39.36. Na pag kinompute natin sa calcu, ang sagot ay, tama ba ang ating sagot? Yes! Amazing grace! So, i-recap lang natin paano sinolve yung problem na to. Actually, ito yung problem kanina. Na-compute na natin yung kanyang equivalent noise resistance na magkano? 2518. Since ipinapahanap ang noise figure, kailangan natin yung equivalent noise resistance na hindi kasama yung input resistance ng amplifier. Ito yun, no? Kasi po, yung first stage, yun ang magre-represent sa input amplifier ng buong stage na yun. Kaya ang ginamit nating RT ay yung input resistance ng unang stage na 600. So gamit yung equivalent circuit natin kanina, na compute natin yung noise factor. 1 plus R equivalent over RA. Bakit po ito yung ginamit na formula? Kasi mismatched yung condition. Ayun, 50 kontra 600. Medyo malaki na yung gap nila. So malaki yung mismatch. Kaya pwede na natin gamitin itong simplified formula ng noise factor. Then after that, kinonvert mo lang siya into dB para makompute ang corresponding noise figure. O, di ba ang dali lang? Yes! Madali lang. O, sagutin natin ang tanong na ito. Ano daw ang noise factor ng isang ideal noiseless amplifier? Oops! Kanina nabanggit ko yan sa aking discussion. Kung natatandaan ninyo, kung ang isang amplifier ay noiseless, kasi ideal siya, it doesn't add noise to the system, anong nangyayari? Yung signal to noise ratio sa input at signal to noise ratio sa output, parehas lang yun. Kaya pag dinivide mo, ang makukuha mong noise factor ay 1. So the answer is 1. Diba kasi nga ideal? O ngayon, paano kung hindi na ideal ang amplifier? Diba? Kung hindi ideal ang amplifier mo, it adds noise to the system. O mag-drawing ulit tayo. Yan yung amplifier mo na may gain, no? May papasok na signal sa input, may noise sa input. Natural sa output, magkakaroon ng signal kasi ma-amplify siya. And then yung output noise, may makukompute din tayo. Kung ideal ang amplifier, itong signal to noise ratio sa input equal sa signal to noise ratio sa output. Kaya ang makukuha mong noise factor ay 1. Kasi pag dinivide mo ang dalawang signal to noise ratio, equal sila. Kung ang amplifier ay practical, no? Typical amplifier na alam natin, nagge-generate siya ng noise. Saan mas malaki ang signal to noise ratio? Sa input o sa output? Pag-isipan yung mabuti yan. Kung ang isang amplifier ay hindi noiseless, meaning, nagke-create siya ng thermal noise. So, yung noise factor natin, hindi na 1. So, saan mas malaki ang signal to noise ratio? Sa input or sa output? Ang pag-isipan mo. O ngayon, ito ang sagot. Pwede ka na bang marinig? Kung ang amplifier ay hindi ideal, meaning, siya ay nagge-generate ng noise, saan mas malaki ang signal to noise ratio? Sa input or sa output? Ang tamang sagot, mas malaki ang signal to noise ratio sa input. Bakit? Remember, kapag ang isang amplifier ay nag-generate ng noise, yung F natin ay greater than 1. Diba? Now, let us discuss the noise generated by a cascaded amplifier system. Kanina kasi pinakita ko sa inyo, posible na yung amplifiers connected in cascade, ang na-compute natin doon, equivalent noise resistance. Diba? So, ngayon, what if yung amplifier mo connected in cascade? Ano ang total noise figure nun? No? Kasi kanina, pagko-compute natin, isang amplifier stage lang. Nako-compute natin ang corresponding noise figure. Paano kung sila ay dugtong-dugtong, connected in cascade, just like this? Ano? So, we have the first amplifier stage, the second, and the nth amplifier. So, of course, we have the signal-to-noise ratio at the input in dB. Kung alam natin ang total noise figure ng tatlong ito, no? Mako-compute natin ang signal to noise power ratio at the output. So, para makuha natin ang signal to noise ratio at the output, then, kailangan muna nating makompute ang overall noise figure, which can be determined using what you call the Friis formula. So, ano po yung Friis formula na yan? Yan ang formula na nagagamit para makompute ang overall noise factor ng isang amplifier system connected in cascade. Okay? So, the total noise factor is due to the noise factor of the first stage. Ito, noise figure. Naka-dB yan. Ito, F lang. So, means factor siya. Okay? So, this is the noise factor of the first stage plus F2 minus 1 over A1. Noise factor nung pangalawang stage minus 1 over A1. And then F3 minus 1, A1, A2. So, you can predict that there is a pattern. Kung merong pang-apat, F4 minus 1 over A1, A2, A3. And so on. Okay? So, mapapansin natin dito, alin sa lahat ng stages, again, ang may pinakamalaking contribution sa total noise factor. It is the first stage. Ano po? Bakit? Kasi yung contribution ng second, third, at saka succeeding stages dyan, lumiliit kasi meron silang divisor. Diba? Kagaya kanina, dun sa equivalent noise resistance. Ang may pinakamalaking ambag or contribution ay ang first stage. So, lagi po natin yung tatandaan. Kaya, yung first stage ng isang RF amplifier, yung front end, napaka-critical nun. Meron nga tayong mga amplifier, ang tawag ay LNA. Ano yung LNA? Low Noise Amplifier. Kasi pinakamalaki po ang impact noong first stage. Kung ang first stage, malaki agad ang noise factor, then yung overall na makukuha nating noise factor, malaki din. Kung maliit ang noise factor nung unang stage, overall noise factor will also be small. Okay? And remember, the ideal value is 0. So, the closer to 0, the better. Pag na-compute mo ng total noise factor, i-convert mo lang yan in dB. So, 10 log of this will give you the overall noise figure. So, this is the total or overall noise figure for an amplifier system connected in cascade. 10 log of the overall noise factor. Ngayon, kung alam mo na to, makukompute mo na ang signal to noise ratio sa output. Bakit? Kasi po, remember, ang noise figure ay signal to noise ratio sa input minus signal to noise ratio sa output. Okay, so ano ngayon? Ang signal to noise ratio sa output ay equal sa signal to noise ratio sa input minus the noise figure. So, tandaan po natin ha. Let us solve sample problem here. Okay, meron daw tayong dalawang cascaded amplifiers. Ang noise factor ay 5 at ang gain ay 10. So, that means identical yun. Ang noise factor nung dalawa parehas 5 at ang gain nila parehas 10. Ano daw ang total noise figure? Okay. So, kunin muna natin yung noise factor equivalent. Ano? That is equal to F1 plus F2 minus 1 over A1. Okay. Wala naman tayong third stage. So, dalawang terms lang ito. No? So, F1 is 5 plus 5 minus 1 over the gain, which is 10, equals 5.4. 5.4. However, factor pa lang yan. So, kung gusto mo makompute ang noise figure, 10 log of 5.4. So, ang sagot 7.32 dB. O, di ba? Ganun lang po kadali. Ano? Kailangan lang familiar tayo sa formula. Kasi usually, ang mga problem solving na ito, direct substitution naman po. Okay? For 3 cascaded amplifier stages, each with a noise figure of 3 dB. So, ang NF niya ay 3 dB. So, yung F niyan, malamang 10 raised to 0.3. At ang power gain niya daw ay 10 dB. Or, as a ratio, 10 raised to 10 over 10, 1. Oh, so, 10. 10 din. Okay, so computein muna natin yung noise factor. 10 raised to 0.3. 1.995. I-store natin ha. So, to get the noise factor, that's F1. So, 10 raised to 0.3 plus 10 raised to 0.3 minus 1 over A1 plus 3 stages. So, 10 raised to 0.3 minus 1 over A1 times A2. So, 10 times 10 equals. So, in calculator, kapag kinumpute natin yan, ang makukuha nating value ay 2.1. So, makukumpute natin yan ang noise figure in dB. 10 log of, sa calculator, hindi ko po i-round off yan. Ano? 3.23 dB. No? 3.23 dB. So, ayun. Tama kaya tayo? Yes! O, di ba? Ang dali lang. O, kanina, 2 stage. O, ngayon, 3 stage naman. So, kahit ilang stages pa yan, yung formula lang na yun ang gagamitin mo, yung Friis formula. Makukompute mo na yung overall noise factor. O, baka magkamali ka, ang unit dito, hindi pa naka-dB. Unitless pa lang yan, ha? So, kung gusto mong noise figure, itanlag mo siya. Okay, so, last example for this topic, ano, yung noise figure na yan. We have a 3-stage amplifier that has a 3 dB bandwidth. No, 3 dB bandwidth of 200 kHz determined by an LC tuned circuit. Okay. So, yung mga previous problems natin, walang nabanggit na LC circuit. Ano po? So, ngayon, ano kaya ang magiging effect ng LC circuit na yan sa ating computation? Actually, meron. Dito, pag tayo ay nag-compute ng bandwidth, ang gagamitin natin ay hindi 200 kHz. Bakit po? May effect yung LC circuit. So, ngayon, ano na yung magiging effective bandwidth natin? So, the effective bandwidth na gagamitin natin sa pagko-compute ng noise power is pi over 2 times 3 dB bandwidth. Okay? So, kunin natin yung effective bandwidth. Pi over 2 times, we have 200 kilohertz. The answer is 314.16. So, ano conclusion? Kapag ang isa pong amplifier stage ay may kasamang LC tuned circuit, yung effective bandwidth ay lumalaki due to the effects of reactive components. Ayan. So, sunod. Ang operating temperature niya ay 22 degrees Celsius. The first stage has a power gain of 14 dB, noise figure of 3 dB. Then the second and the third stages are identical with the gains of 20 dB and noise figure of 8 dB. The output load is 300 ohms The input noise is generated by a 10 kilo ohm resistor. So ito yung noise generator mo. 10 kilo ohms ang kanyang noise resistance. Unang tanong, ano daw po ang noise voltage at ang noise power sa input, output ng amplifier? Assuming ideal at noiseless yung amplifier. Okay, so isa-isahin natin. Ano po? Yun munang noise power doon sa input. Ang noise power sa input ay equal sa KTB. May calculator naman tayo. Aray ating save. Shift store A. No? So, aray ay nakastore sa A ng calculator. No? Irekta na natin ito sa calculator ngayon. The answer is 1.28 to the negative 15. 1.28 to the negative 15 is femtowatts. So, yan po yung una, ano? Ito na yung noise power. How about the noise voltage? Noise voltage at the input ay square root of 4 KTBR. So, since na-compute na natin ito, yung KTB, i-store natin yan sa B ng calculator. O yan, para hindi mo malimutan, lagay mo na sa B ng calculator. So, we get the square root of 4 times yung KTB, which is stored in B, times yung R. Ano yung resistance na nag-generate ng voltage? Ito, 10 kilo ohms. So, 10 kilo ohms equals 7.15. 7.15 microvolts. Papalagay natin, lagay mo ito sa alpha C ng calculator. Shift, store C. Nakuha na natin ang noise voltage sa input, noise power sa input, yun namang output. The noise power is equal sa noise power sa input times yung gain. Overall gain yun. Bakit? Kasi tatlong stages yan. Ano po? Kunin muna natin yung total gain. Anong sabi niya? Yung una daw, ang gain niya ay 14 dB. Yung second at saka third ay, ano ang gain niya? 20. So, plus 20 dB plus 20 dB. So, ang total nito ay 54 dB. Okay? Yan po ang power gain. So, pwede natin kunin yung power gain as a ratio. The gain as a ratio is 10 raised to 5.4. Okay? Compute natin yan. Yan. So, we have 251188.64. Para hindi tayo malito, i-save natin yan sa D. So, na-determine na natin yung gain. Anong sunod natin makukuha? Makukuha na natin ang noise, power, at the output. Ito na yun, ano? So, that's equal to the noise power at the input times the overall gain. Since nakastore naman sila sa calculator, pwede na nating erekta. Ang noise power at the input is nasa B at yung gain ay nasa D. So, ang sagot 3.21 to the negative 10. 0.32, no? 3, 2, 1. Anong unit? 2 to the negative 12. So, 0.321 is to the negative 9. Nanowatts. Ayan. Paano natin makukuha yung noise voltage sa output? Pwede ba na ang gawin ko yung noise voltage sa input? Multiply ko nung gain? Hindi. Bakit? Kasi power gain to eh. Power gain ito. At ang nakuha mo ay noise voltage. So, paano ko makukuha yung noise voltage sa output? O di mula sa noise power sa output. Because we know that power is V squared over R. So, kung nakuha mo ang noise power sa output, that is equal to VNO squared divided by R. So, kung kukumpute natin yung noise power sa output, that's the square root of NO times the resistance at the output. Ano? Shift, store, E. Para po, yung sagot natin na to, yan, nakalagay yan sa E. Gagamitin natin yan eh. So, square root of yung alpha E, kasi doon nakasave ang noise power sa output. No? Multiply natin ng R. Ano ba yung resistance sa output? The output load is 300 ohms. So, yan. May makuha tayo ngayong 310 microvolts. Ayun. Tama po ba? Yes. Or 0.31 millivolts. Ayan. So, tama naman yung nakuha nating sagot. 1.28, 7.15, 0.322, tapos nanowatts, tapos 0.322 uli millivolts. Na ginawa nating 310 microvolts. Okay. Ito, baka gamitin natin mamaya. Store natin sa F. So, nasolve na natin yung letter A. Okay? Next. For letter B, ano daw ang overall noise figure? Ang overall noise figure, makompute natin mula sa noise factor. Diba? Yung Friis formula. Kunin muna natin yung noise factor, which is F1 plus F2 minus 1 over A1 plus F3 minus 1 over A1, A2. So, yung value ng F1, ano ba ang kanyang noise factor? 3 dB ang noise figure. So, 10 raised to 0.3 ang noise factor niya. Diba? Plus, yung F2 natin, ano po ang kanyang noise figure? So, 10 raised to 0.8 minus 1 divided by the gain of the first stage. Power gain daw ng 14. So, 10 raised to 1.4 plus for the third stage, di ba identical yung second at third stages? So, ang noise factor niya, 10 raised to 0.8 pa rin. Paminusan mo ng 1 divided by yung gain ng unang stage, 10 raised to 1.4 times yung gain ng pangalawang stage, 10 squared. Okay. Pag kinumpute natin 2.21, no, ang noise factor, 10 log of the answer, we have 3.4. The answer is 3.44. Sagot dito. 3.45. Hindi naman nagkakalayo. Siguro surrounding off lang yun. Ano po? So, nakuha na natin. Sunod, overall noise figure. For letter C, actually same problem lang yan. Sa letter C, ano naman ang hinahanap? Actual noise power at noise voltage sa output. So, paano natin makukuha ang actual noise power sa output? Dito tayo gagamit ngayon ng overall noise factor. 'Di ba? Ang overall noise factor equal yan sa signal to noise ratio ng input divided by signal to noise ratio ng output. Okay? Gawin natin ha. Signal sa input divided by noise sa input over signal ng output over noise ng output. Pwede natin yung isimplify. Signal to noise ng input times reciprocal nito, noise ng output over signal ng output. Okay. Alam natin yung overall noise factor, di ba? Remember that the overall noise factor is 2.21. Equal ito sa overall noise factor. So, to solve for the noise power at the output, we have the overall noise factor times the noise power at the input times the signal power at the output divided by the signal power at the input. So, signal power at the output divided by the signal power at the input. Okay. Nakastore ba lahat yan sa ating calculator? Yung F natin, ang overall noise figure is 2.21 times ang noise power at the input, saan po nakalagay? Sa B, times signal sa output over signal sa input. O, di ba yung output over input, yun yung gain na nakastore sa D? Yes. Okay, so we have 0.71 nano. 0.71 nanowatts. Okay, so 0.71 approximately nanowatts ang noise power at the output. Okay, sunod. Ano naman ang noise voltage sa output? O di gamitin ulit natin yung power is equal to VNO squared over R. Okay? So to get Vn at the output, that's the square root of NO times R, or 462 microvolts approximately kung tayo po ay magra-round off. Okay? So, let us check kung tayo ay tama. Tama naman, 0.711 to yun, yung nakuha natin kanina, nanowatts, and we have 0.462 millivolts. Ang sagot natin naka-microvolts lang, pero parehas naman sila. Okay? So, ayun po, medyo mahaba yung solution dito sa problem na ito kasi marami yung hinahanap. Meron tayong ABC. No, kanina, sa letter A, kinonsider natin na siya ay noiseless. And, since ito ay may noise figure, sa letter C, kinuha natin yung actual noise power sa output. No? At actual noise voltage sa output. Galing sa noise figure. So, kinumpute lang natin yung noise figure, and then after that, kinonvert natin sa noise factor. Kasi hindi mo naman magagamit directly ang noise figure. So, ang ginamit natin yung value na 2.21 noise factor. Signal to noise ratio ng input divided by signal to noise ratio ng output. Okay po. Now, let us go to the last figure of merit na ginagamit sa pag-evaluate ng noise performance ng isang circuit. Ito ang tinatawag na equivalent noise temperature. So, ang equivalent noise temperature, parang noise resistance, hindi rin siya totoong temperature. This is just a fictitious temperature na ginagamit para i-indicate kung gaano karami yung noise na na-generate ng system. Saan usually ginagamit ang noise temperature? Ginagamit siya doon sa mga sophisticated VHF, UHF, microwave, and satellite radio receivers kung saan dapat ang noise ay maliit lang. So, hindi pwede na sobrang dami ng noise sa mga systems na ito. These are high-end microwave frequency circuits na dapat mababa lang ang amount ng noise na present. Kasi usually digital yung mga yan Kaya dapat ma-minimize natin yung noise. So, dun sa mas sophisticadong systems, mas ginagamit ang noise temperature kumpara sa noise figure. So, here is the formula for finding the equivalent noise temperature. Equivalent noise temperature TE is equal to TO times F minus 1. So, dito yung TO, yun yung ambient temperature. Na pag walang nabanggit, 290 kelvins. Ito namang F, yung noise factor. So, kung naka-noise figure yan, naka-dB, convert mo into noise factor. Diba yan yung 10 raised to yung noise figure, divide mo lang ng 10. O, yun na. Diba? Parang gain. 10 raised to, yung gain, dinidivide natin ng 10. Okay? So, problem. We have a microwave receiver that has a noise temperature of 145 kelvins. Ano daw ang noise figure? So, for the noise figure, that is equal to 10 times log of the noise factor F. Diba? So, from TE equals TO times F minus 1, makukompute natin yung F. Yung Fi equal sa TE over TO plus 1. Sa calculator, idiretso na natin yan. 1.76 dB na yan. So, this is 1.76 dB. Hindi ko na kinuha ang noise factor kasi hindi naman siya itinatanong. Direct ako na po. So, tama ba tayo? Yes. Next. Determine the noise figure for an equivalent temperature of, parang yung kanina, So again, the noise figure is 10 log of TE over TO plus 1. Diba? So, compute natin sa calculator. 0.9989. So, this is approximately 1 dB. Diba? Next, ano naman daw ang equivalent noise temperature kung ang NF ay 6? Kung ang NF ko ay 6 dB, malamang ang noise factor ko 10 raised to 0.6. Diba? Okay, gawin natin yan. Ang equivalent noise temperature ay TO, wala naman nabanggit, so 290 na rin, times 10 raised to 0.6 minus 1. Okay. So, sa calculator, the answer is 864.5. So, the unit of course is kelvins. Kung gusto mo naman na naka-Celsius para mas madali mong ma-imagine, minusan mo ng 273. So, the answer is 591. 591 degrees Celsius ang katumbas niyan. So, anong ibig sabihin? The higher the temperature, the more noise present. Yun po ang ibig sabihin nun, no? Pagtaas ng noise temperature, pagdami ng noise ang na-generate. Okay? A receiver connected to an antenna whose resistance is 50 ohms has an equivalent noise resistance of 30 ohms. Ano daw ang noise figure in dB at ang kanyang equivalent temperature? So, pwede natin gamitin yung formula na ang Fi equals sa 1 plus R equivalent over RA. Ano? Yun yung antenna resistance. So, we have 1 plus, ang equivalent resistance ay 30 divided by antenna resistance na 50. Mismatch naman sila eh, di ba? Pagkalayo, 30 at 50. So, the answer is 1.6. Noise factor yan. So, in dB, the noise figure is 2.04. 2.04 dB. Okay. Now, anong equivalent noise temperature? O edi yung TE, makukuha natin. TO, wala namang nabanggit na temperature, di ba? Kaya, ang gagamitin natin ay 290 times F 1.6 minus 1. So, we have 174 kelvins. So, yan ang ating equivalent noise temperature. Okay. Tama kaya tayo? Yes. Ayan o. Yan yung sagot. Okay. So, now, let us have the last problem for this video. We have a satellite receiving system that includes a dish antenna. Yung dish antenna, ang equivalent temperature ay 35 kelvins. Connected via a coupling network. Na ang equivalent temperature ay 40 kelvins. Tapos connected siya sa isang receiver na ang equivalent temperature naman ay 52 kelvins referred to its input. What is the noise power at the receiver's input over? Kapag kinumpute mo yung power sa receiver input, hindi lang dapat yung power sa input ng receiver ang computein mo. Kasi nag-ambag yung antenna at yung coupling network. Ano? So, to solve for the total noise power, o ID, ang total power ay power galing sa antenna plus power galing sa coupling network plus yung power ng noise galing sa receiver, input ng receiver. Diba? Okay. Alam naman natin na ang formula ng power, lahat yan ay equal sa KTB. Diba? So, ang mangyayari, the total power equals K T1 para sa antenna B. Common naman sila ng bandwidth. Ang sabi dito, 1 MHz yung bandwidth plus K T2 times the bandwidth plus K T3 times the bandwidth. So, obviously, the sum is just K T1 plus T2 plus T3 multiplied by the bandwidth. Ano? So, pwede na natin yung computin sa calculator. So, ang sagot po ay 0.175 nanowatts. So, kung gusto mo naman ng nakapiko, 175. 175.26 pico watts. Ayan. So, that's the noise power at the input of the receiver. Next, ano naman daw ang noise figure? Alam naman natin guys, ang noise figure ay signal to noise ratio ng input minus signal to noise ratio ng output. Wala naman tayong ganyang details, diba? So, paano yan? Ano pa ba ang given about the receiver? Ang receiver daw ay may nabanggit na noise temperature referred to its input. O may makuha ba tayong noise figure mula sa noise temperature? Yes. Ano? Remember na meron po tayong formula na TE is equal to TO times F minus 1. Okay? So, yan yung ating equivalent temperature. Ang sabi, yun daw mismong receiver. Ayan, microwave receiver. Ang hinahanap niya, determine the receiver's noise figure. Ayan. So, pwede natin gamitin yung noise temperature ng receiver na magkano? 52 kelvins. Para makompute yung noise factor niya. Diba? So, yung noise factor niya ay magkano? Ang noise factor ay 1.18. 1.18. Pero unitless yan. Ang hinahanap noise figure. So, in dB, the noise figure is 10 log of this. 0.716. 0.716 dB. Or pwedeng gawin mo ng approximately 0.72 dB. O ayan, parehas lang tayo ng sagot. 0.716 dB. Okay? So, tapos na po. This is the last example problem for this topic kung saan, ano ba ang ating diniscuss sa video na ito. Diniscuss natin yung iba't ibang parameters na ginagamit sa pag-evaluate ng noise sa isang system. Ano-ano yon? Signal to noise power ratio. What else? Noise factor. Ano pa? Noise figure, noise resistance, and the equivalent noise temperature. Okay? Most of the time, ang ginagamit ay noise figure na naka-dB. Pero kapag ang system ay microwave frequencies na yung ginagamit. Halimbawa, microwave communications or satellite communications, kung saan dapat napakababa ng noise, ang ginagamit po natin ay equivalent noise temperature. Yun yung mas common na ginagamit. Okay? So, that's it. Mag-practice na lang po kayo na mag-solve ng mga problems na makikita sa mga end of chapter ng mga books natin. Yung mga textbooks na binanggit ko sa inyo para bago tayo mag-long quiz, kayo ay well prepared. Okay? Until next time, bye-bye!